component. So V naught I have used V infinity. So with this, you have first to calculate or obtain an expression for Vy. So how would you do it? Vy, this is a boundary layer approximation. This can be regarded as roughly a good fit of the f prime of eta actually. If you recall, f prime of eta. Eta was defined suitably in the class. I don't know, remember the definition. Right? So how would you get Vy, the y component of the velocity? Can you check your notes and see how you get the, I'm getting the answer for that in the notes. You recall we had this expression for Vy. So now how would you get Vy? Using this expression, how would you get Vy? What do you need to get Vy? F of eta. So we have seen that this can also be written f prime of eta. Actually, this should be f prime of eta. This can also be written as 3 by 2 and eta by 4.64 minus half eta by 4.64 cube. This is just another way of writing it. You're supposed to check this, right? So clearly, one way is to integrate this, use this form and integrate this and find f of eta, but you get a constant, integration constant. So how would you evaluate the integration constant? So from this, I can very easy to integrate this. F of eta is equal to something plus some constant. So how would you evaluate the constant? What do you need to evaluate the constant? The value of f. So what is f at eta equal to 0? You have to check that, right? You can easily figure out f of 0 actually was 0. So you constant will not be 0. Another method, without worrying about the eta now, because you have now given, and of course delta is a function of x. Right? Another way is to get Vy directly from the continuity equation. So from this, clearly dvy by dy is minus dvx by dx. So now I can integrate this with respect to y. The function of both x and y. So, but I can integrate it with respect to y, and this will give rise to some function of x. Let us say, since f is already used, some function of x. So first you have to calculate dvx by dx, right? So can you calculate it? Piyush, when you come to the board and carry out this integration, first calculate dvx by dx. dvx by dx. You get a v infinity. Yeah, so delta is a function of x. That you can assume it's given. But you can write the answer also in terms of d delta by dx and leave it like that. Y over delta, y doesn't have to be, what is d by dx of 1 over delta? Minus 1 by delta square d delta by dx. And then calculate the other term. Over delta square, that is. Yeah, what are you, why you get 2
times y delta to the power 4 or 4. It would be 3 by delta to the power 4.
Yeah, I don't know what you meant.
It's cubed.
Y square you should get, that is not been differentiated.
It's cubed. The expression is cubed, not square. The first expression. It's cubed.
So it's
Cubed different.
Yeah, I'm sorry, it's cubed. Okay, so there's nothing you have to do with y, that's a constant. So you will get minus 3 by delta over 4. I think you have to be a little bit more, conversant with doing these derivatives. Anyway, yeah, but I'll complete the problem. Right, so all I have to do is to integrate, differentiate this first with respect to x. So dx by dx simply be infinity 3 by 2 y minus 1 over delta square d delta by dx minus half y cube, right? So this would be minus 3 by delta power 4 d delta by dx. That's how there is to it. So we get 3 by 2, we can take a lot of common factors, and finally I can write d dy by dy minus of this actually, right? And it can be written as 3 by 2 d infinity times divided by delta times d delta by dx, and then I'll have within bracket y over delta minus 4 cube. This is dvy by dy. Right? And so now I have to integrate this. So dy would be this integral with respect to y plus some function of x, because only a partial derivative and dy is a function of both x and y. So easy to do the integration with respect to y, right? I'll probably give the answers to some of these problems on Thursday, but and you can easily show that actually that function of x is 0 by using the boundary condition that dy of 0 x is 0. That's the no-slip boundary condition, part of the no-slip boundary condition. So you get the final answer quite easy. Now dy is not going to be of much importance, but you should know how to get it to complete the problem, right? So the next question is more important, the numerical problem. For that we need all the formula for the Reynolds number that all that you already know. So Rex is is this, right? And then delta by x is 4.64 Rex power minus r. So these expressions are not given, but they were given in the class. So you can easily see what is you're given that kinematic viscosity is and you have to calculate Rex and delta at x is equal to 0.1 m. Okay, you tell me what Rex is and what is delta. Calculate and then 10 power 5 and delta obviously is at 0.1 m. So at x equal to 0.1, delta is 0.1 times 4.64 times 10 power 5 minus half it is. And that turns out to be 1.47 10 power minus 3 meter. Okay. So the main calculation is also the vorticity you are asked to calculate. So clearly it is only Vx and Vy are the only non-zero components, and they are dependent only on x and y. You can easily verify the vorticity vector would be given by Ez times dvy by dx minus dvx by dy. This is what you have to calculate, right? So clearly, when you are asked to calculate it at y over delta is equal to 0.25 and at 0.75. So you are also asked to negate as a first approximation this term. You can also calculate it because we obviously have expression for Vy, and you can calculate dV by dx and convince yourself that that will be much smaller than dvx by dy. We have seen that the gradients in the y direction are expected to be much more than that in the x direction. So it will be a somewhat cumbersome calculation to calculate a small quantity, right? So you might as well leave it at this. So approximately minus Ez, so in the z direction, dvx by dy. So what is dvx by dy? Right? dvx by dy is b infinity 3 by 2 delta, right? Because that's the first term, and then minus half now I have to differentiate, right? So it will get 3y squared. So it can be compactly written as minus Ez times 3b infinity by 2 delta and 1 minus. In this form, you will clearly see that the vorticity is the maximum at what value of y? At y equal to 0, right? And that value is 3b infinity by 2 delta. So what is that value you can calculate? Right? So 3 times 1 by 2 times 1.47 into 10 power minus 3. So what is it? It's in the units. It's clearly meter per second. It's actually per second. Unusual units. Right? So per second is the unit. So this is the maximum value of the magnitude. I'm talking about the magnitude. It is minus Ez, the negative z. I think we are more worried because we have seen the vorticity is created at the boundary by the no slip boundary condition, the maximum difference in velocity you will get. So that maximum vorticity, and you can clearly see that this approximate formula, it simply vanishes at y equal to delta. So at the boundary layer, it becomes 0. So there is a diffusion of vorticity, right? So this value, you can easily see it is what I am getting is 1020.4, and if you calculate these, this one is 956.6 and this is 446.4. You can see the vorticity magnitude. I'm not having the sign, but the vorticity magnitude, right, is given by progressively decreasing as we go towards the boundary. So that's the main. The calculations are very simple, but you have to be very careful about the units, right? And these half and coefficients and so on, right? This is mainly to show that the calculation of the vorticity, and I leave it as an exercise for you to actually calculate this. You will find that it's a very small value. It may be a good exercise in doing this differentiation and then substituting the numbers and calculating. I don't have the final answer, but you can do it and convince yourself. You're getting a value that is very small compared to this, order of magnitude smaller, then probably your calculations are at least grossly right. Right? So that's what you have to do. Are there any questions? The other problem given in the assignment, it is I don't have the exact problem from words to the number, but it is from BSL. So that has nothing to do with boundary theory, and the solution is fairly straightforward. Because what you are asked to assume is a cylindrical coordinate. So you have to do it in the annulus between two cylinders, right? One radius kappa times r, another at r, and you are already given the rotated, and on top of it, the fluid is also being heated because of the difference in temperatures between the inner and the outer cylinder. So there is a temperature gradient also. Again, if you assume constant viscosity, so we have already solved this problem, V equal to cylindrical coordinates, and we have made so many approximations that we find is a function only of RC. So we have solved it. And so, the first step is you have to calculate the second invariant of D, that is phi D, and you can easily verify that the only term that would contribute is D phi RC, D to D RC phi. There will be some derivative of involve d phi as well as its derivative with respect to RC. You have to go to the tables, the formula sheet, to find out what that is and calculate phi D. And finally, the assumption that the axial conduction term can be neglected and you can consider E to be a function of RC alone will considerably simplify the problem, because what you will find in this, you will get K by RC and D by dRC, RC dt by dRC plus the viscous dissipation has been included. So here you will find that in this problem we can actually solve it using the viscous dissipation term, because this turns out to be 0. You will find because the V is only d phi component is present, the temperature doesn't have any variation in the phi, you are assuming it, right? So you will find that this term would be 0. So you get an ordinary differential equation in T in terms of RC. And of course, if you neglect the viscous dissipation term, we get pure conduction without any motion of the fluid. That is a very standard in heat conduction problems you would have done. Solid heat conduction normally, right? Where only conduction is there. Here, because the fluid is stationary and not moving, that is what you would get. You won't get any contribution from the viscous dissipation. And you can get that also. The answers are given in vertical Lightfoot. I'll give you a summary of the answers in the next class. It's quite easy to solve. The boundary conditions are the temperatures are given at the inner and outer cylinders, and that's very straightforward to apply. So I don't want to spend too much time on this problem. It's a very straightforward exercise. You can verify that this is equal to 0 for these two conditions. That's why it is 0. And so, and then you neglect the axial conduction term here, as we have always done for a long cylinder. Then you can take, you have to calculate this, the viscous dissipation term, and then simply integration would be straightforward, because this would be a function of RC alone. Right? So you can easily integrate the equation and get the temperature profile between the inner and the outer cylinder of the fluid. Right? So that's the problem. Are there any questions? Any questions? So we'll move on to assignment 8, and I want to spend some time on the first problem. It's again from Lightfoot. So what here we have is we have already seen the flow between two parallel slits, right? And here, so I'll assume this to be, let's say, the inlet here, and Z is equal to 0. This is the x direction, x equal to plus b and minus b. And so the flow, one dimensional flow, you can easily show that Bz is Bz max times 1 minus x over b squared. It's very similar to the cylinder problem that we had. So what he's saying is that now there's a constant heat flux that is provided at both the walls. We can assume that it's being heated for convenience. So Q0 is greater than 0. Right? And then the temperature of the fluid entering is uniform at the entrance at Z equal to 0. Let's say Z equal to 0. The temperature is T1. So then you have to obtain the differential equation for T, which varies with x as well as z. And then where the viscous dissipation effects are included, the axial heat conduction term is neglected. Right? So the differential equation is rho Cv first in the most general form. I have to evaluate that, and you can easily verify. Even though this is a simple rectangular coordinate. So Bz is the only term that's present. So this can be immediately written as dE by dz. So rectangular coordinates, the other term is k times the Laplacian of the temperature, and you also neglect the axial conduction. You actually have to take it along only the, so this would be d squared d by dx squared. Now you have to calculate the viscous dissipation term, right? And you can easily, so now the viscous dissipation is easy to write down, as we have seen underneath. This will be minus 4 times the viscosity times, and finally, as I said, it's easily written as first you have to gather together all the diagonal terms 2 by 2 at a time. Minus, right? Then you get all the off diagonal terms one with each other. So this would be D12, D21, D13, D31, D23, D32. Obviously, because D is a symmetric tensor, I can write it as D12 square, D13 square, to D23 square. I can assign 1 as x, 2 as y, and 3 as z. It's very easy to write down the formula for, D can be very easily written in, this would be dB dx by dx, and this would be dy by dy, so that the trace would be the divergence, right? And clearly, so you have dz and it's a function of x alone, so you expect only the, even looking at it, you can see that it is going to be only the dxz that is going to come into play. So this would actually, so I am not going to write all of this, it will all be 0. Everything in fact would be 0 except that dz or dxz would be half dx by dz plus dvz by dx. Right? And so here dvz by dx is the only term that is there. So this would also be 0 because dx itself is 0. So all I am going to get in this, all of these terms would vanish except this dxz square, right? So that would be minus dxz square or dzx square. That would be minus times 1 over 4 dvz by dx square. It's almost looking like the case for the cylindrical word. There also will be z, and z more or less matches with the z in the Cartesian. So dvz by drc square, we are getting dvz by dx square. That's the only difference. Right? So clearly this would now be minus 4, that would be plus the whole square. This is very easy to estimate. So dvz by dx is dz max times minus 1 over b square times 2x. Right, so this would be plus 4x squared by b power 4 actually. And then I have k times d squared d by dx squared, and then I have rho cv dz max times 1 minus x over b squared dt by dz equal to this. So this is the differentiation. The procedures are very much similar to what we had for the flow down cylindrical tube, and all the arguments thereon are then now again is introducing the Q naught here. It is instead of R by K, it is simply B by K. Here we use the dimensionless variables, and then psi or sigma is saying is x over B, and then Z is suitably defined. The zeta is again suitably defined as k times z by rho cv bz max times b squared. We put all these into the equation. The final equation is what I am going to write down, and I leave it as an exercise for you to do it. You will get an equation very similar. What you should get. Anyway, we are going to neglect the viscous dissipation for the further calculation, and again we are going to calculate only the asymptotic solution. Very similar. So what he is saying is that assume is this is sigma here. That's the only difference. Now what are the boundary conditions? Right. So the boundary conditions. Clearly, one boundary condition is that we need. So we have here one derivative with respect to z and two derivatives with respect to x. The long cube in one direction, and of course I have the boundary for x very clearly defined. No doubt about that. So I need conditions at x equal to minus b and x equal to plus b. And so, what can you say about t what is the one boundary condition at z equal to 0? What is that? Is equal to T1, that's given, uniform, right? That means they're doing the same for all x at the inlet, right? So what does this mean? So theta at sigma 0 would be what? Would be 0. So what can you say about the boundary condition for? So I have two boundary conditions, x equal to minus b and x equal to plus b. What would be the boundary condition? The flux boundary condition. K dt by dx. Can you write the two boundary conditions? At x equal to minus b and we want at x equal to plus b. So there we had R equal to RC with one boundary and we imposed a finite temperature at the R equal to 0 which we later on used, RC equal to 0. Here it's slightly different because there are two boundaries at x equal to minus b and x equal to plus b. There it was at the center of the cylinder and where is it? The negative or equal? So you think the sign is the same for both? No, why do you write it then? What is k dt by dx? Determine that this is actually that which is correct. I mean, what is the principle that is used here? You have to be very careful because there I think quite give a satisfaction. I just said it will be whatever the value of Q naught is. Whether it's positive or negative, you will get K dt by dRC is equal to Q naught, right? And no one raised an objection also at that time. But now here, the boundary conditions are. You have two boundaries, right? The principle that if you want to do it, this is often referred to as a continuity of flux. That's somewhat misleading because on the one hand you have a flux vector and you also have a flux scalar, which can have a sign, right? So the sign convention can be somewhat confusing. What it really says when you have a boundary like this, because outside the cylinder you are providing heat to whatever means. Right? Inside not the cylinder, inside there's a fluid, right? The principle which will lead to an unambiguous equation is that if you assign, I find it convenient to assign a certain direction to Q naught. So you can assume either it is heated or it is cooled, right? So when it is heated, as I said, I put an arrow here, that means Q naught will be greater than 0. So it's better to choose one, whatever is the situation, or you can do it separately for both, right? So if I choose Q naught to be greater than 0, that means heat is coming in, it is being heated, the slits, the wall of the slits is being, walls of the slit is being heated, right? So the idea to be used is that the heat entering the surface from one direction must be equal to the heat flowing out of the surface through the other boundary. So you have two parts here, one this, another this. So at x equal to minus b, what is entering is clearly q naught. There's no doubt about that. That is now equal to what must be leaving from the surface into the fluid. That's taking place by convection. Okay, so that is where the k dt by dx will come in. And here it's very important to remember the sign convention. Right? So this is what I am going to equate it to, is the flux that is being transmitted to the fluid from the wall at the wall. Okay. So how do I express it? So there, since it's transferred by convection, so I'll first write minus q dotted with n. That the total heat. So that is minus q dotted with n, and that is the formula. Because I am not going to integrate over the whole area here, because I only want at a particular point, right? And so now I have to ask, what is the direction of the normal for this phenomena of the heat being transmitted to the fluid? N is, it can be either one or the other. It is either minus Ex or plus Ex. So what is it? Is it plus Ex or minus Ex?
X equal to minus b. At x equal to minus b,
X is equal to outward normal. How do you determine what is outward? So you have to know the convention again. So what is outward? If you see, for instance, if you now look at a boundary, you encountered this in the force also. When we say the outward normal, then I am focusing on the body here, when force transmitted to the body from the outside. So then the outward normal is actually coming from the body into the outer region. That is what we call as the outer normal, right? N for transmission of forces. Now here again the same principle applies. So if I want to transfer heat, right, to the body from outside by convection, then over the whole area it will be minus q dotted with n dA. So the minus is coming in because the q traditionally, when you write minus k dt by dx for instance, that corresponds to the q dot n will effectively correspond to the flux coming out of the body. So you have to put a minus, because for this heat coming in to the body is to be treated as positive. Right? So there is a sign condition already there. That is why the minus is used. So I am having minus q dot n. The n is from the body outward. Right? So here the fluid is inside. So from the body, which is the fluid, which is receiving the heat, you have to identify the body that is receiving the heat is the fluid, right next to the wall. Right? So the outward normal would be clearly minus Ex. So I have minus of, right, dotted with minus Ex. Vector Q is minus k times the gradient of the temperature. But you can clearly see, so only whatever it might be, only the component along the x direction is going to play a part, because the outward normal here is minus Ex. Minus Ex or Ex. I am going to get now Q here. So there is already a minus sign here. The Q flux vector, that by Fourier is always minus k times the gradient of the temperature. So I have minus k dE by dx Ex. Thus there might be other terms, but I am not worried about it. Right? And so how many minuses are there? 3 minuses. There's a minus here, there's a minus here, there's a minus here. So it will be minus. So Q naught is actually minus k dE by dx at x equal to minus b.
Did we get a minus sign? Minus q dot n?
No, that is the formula, because that is being transmitted into the fluid, right? So that is itself, because that is the heat entering the fluid. That is automatically taken care of. So the q always by convention, because Fourier since he always use minus k dt by dx, and the q dot n is what is coming in, right? Coming out, sorry, because n is the outward normal. So since for us the heat coming in, right, is to be treated as positive, right? So this is representing the heat coming into the body. This is only the outward normal. The heat direction is coming in, right? So q dot n represents the heat going out, but for us q is the heat coming in, not this q I'm talking about. Total q, heat coming in is given by this formula. So I'm here identifying only this portion, so I only wanted at that one. I'm not going to integrate it now over the whole area, right? This is only flux continuity equation. So that is where the minus sign is coming. Now you can easily see if I do this here, right? Again q naught is coming in, greater than 0 is coming in, so I will treat it as being heated from here also, right? So now this fluid, so the flux entering the surface from the outside, now it is being transmitted from the surface. There are two parts to the surface. That is where the problem comes in. If it is continuous, it is always minus k dt by dx. Here I am having a surface which is separating two parts. One which is the fluid inside the slit, the other which is the outward condition through which the heat is being transmitted inwards, q naught, right? So again heat is transmitted in, and then here the heat is to be conducted from the surface to the fluid, right? So again q naught is equal to minus q dot with n, and you will easily see the only difference would be here, that this outward normal is from the fluid outward into the body that is actually transmitting, right? From the fluid outward, right? So from the fluid outward is plus Ex, and so I get plus Ex, and so here actually for x into the plus b you could get q naught into k dt by dx. So this is very critical. Why the minus is coming? Because there are two sign conventions involved. Common way Fourier defined his flux vector was such as to get the heat transmitted to the body will be given through conduction will be given by minus q dot n dA. You can easily verify that with the Fourier's expression for the heat flux vector, it is minus k dt by dx or minus k the gradient of t. The common idea that heat flows from higher temperature region to a lower temperature will be obeyed. Okay, so that is the crucial part. So there is there's a confusion because of the heat flux vector and the heat flux. Actually, heat flux is a scalar. Then you have all the sign conventions, right? There are some books which might simply divide this as some h or something and this minus would not be there. Then that heat flux vector has a slightly different meaning from what we normally associate. So I am using the conventional way of treating the conduction problem. So this is what you have to remember. So I am identifying here by inject. So this is to be calculated at every point. So at every point the heat that is transmitted is minus q dot n. The n is the outward normal coming from the body to which I am considering the transfer of heat outward. Right? And for q, it could be the Fourier's law, it could be any other law. But you have to understand that finally minus q dot n effectively represents the net heat in. So you have to define the q corresponding. This is basically the Fourier's law, if at all you want to call it a law, without any reference to his particular model for the heat flux vector, which is minus k times the gradient of T. This idea is independent of that. What Fourier effectively said, and that idea is far more important than his special relation, which relates the heat flux to the temperature gradient. That is a very special, just like saying Newton's law of viscosity. It's a very special class. What Fourier effectively said was he proposed the concept of a heat flux vector, right? In such a way, the heat flux vector is defined at all points on the surface of the body to which the heat is being transmitted by convection, he said the heat flux vector exists in such a way that minus integral q dot n dA gives the net heat transmitted to the body through convection. So all of this you have to understand before you can interpret the sign convection correctly and unambiguously for every problem. You can now go back to the cylinder problem and figure out, right? You can consider now both cases here also. Let's say heat is being removed. What will be the boundary condition? Right? In the cylinder also, there is only one boundary, R equal to RC. Right? The heat is being transmitted. You can consider separately, and at the cylinder surface, heat being removed, you can consider separately and convince yourself there. For both cases, the boundary condition would be kdE by dRC at RC equal to R is equal to Q naught. Now for heat being removed, Q naught will be negative. For heat being added, Q naught will be positive. That sign convention also you have to remember. Right? So if I want heat to be removed, what I will do is I will have heat in this. Make use of this idea, heat flowing into the surface, right, is equal to heat flowing out of the surface into the other part of the fluid. So I will call this then minus Q naught as the amount of heat that is being removed. The direction is maintained, heat is being removed, but we want positive heat to be removed. That would represent the case heat being removed. But Q naught for us has the convention that Q naught greater than 0 means it is being heated from outside. Q naught less than 0 means that it is being cooled. Cooling is being provided from outside. So I would rather make this as minus Q naught as the amount of heat that is being removed, and then consider here what would be the heat transmitted to the surface from the fluid, right? And you can verify then probably the boundary conditions will remain the same, right? That is the answer to the question of the boundary condition. So the rest of the problem is fairly straightforward. You can easily prove that this would mean that at sigma equal to plus 1, we get D equal to 1 and sigma equal to minus 1, D theta by D sigma is actually minus 1. So now what? Now what you have to do is to apply without the viscous dissipation term and apply this equation, right? So what would the equation look like? From now on, the procedure is more or less similar to what we did for the, it's only the boundary condition, there is a slight confusion. So if you want to write the equation 1 minus, right, d theta by d zeta is simply C naught, and it is equal to d squared sine by d sigma squared. And this is very easy to integrate, right, without the, probably even include the viscous dissipation. Anyway, given the solution only without the viscous dissipation, we will do that. And so you can easily get, using these boundary conditions, you will get that theta is actually given, the formula is given in the question itself. So it will be 3 by 2. This is what I am integrating, that's what I get. So you have still the constant C2 to be determined, and for that he is going to now integrate the equation of motion over a certain boundary. So I can consider a certain boundary, let's say from the inlet. So I want to consider an integral condition, right? So the integral condition would be here. Right? So this would be dx integrate over the volume. Right, is I can write it like this, and then I can write this as u dot n dA. Right, so here I have again to be a bit careful. So this is dx dy dz over the whole volume, right? So dz is a function of x and dt is a function of x and z. So any integration over y, so I'm actually dt by dz, so I'll make it z prime, because I'm going to consider y, let's say width of the plate, right? X would be minus b to b, and z would be from 0 to z prime, would be from 0 to z, an arbitrary length z. Again, you will have to integrate out the dt by dz prime part, because it's a function only of x. So I can integrate that, and what I will get is probably w will be out minus b to b rho cv dz times d of xz minus d of x0, right, dx. The dt by dz prime will get integrated, and there will simply be a difference in the temperature. Now to do the other one, right, minus q dot n dA, that has now to be done for the two parts separately. Probably they will add up to be the same. If both are coming to the constant heat flux q naught, that integration would now be over the area, right? So the area here, because it's constant q naught, so this would give me q naught. I can easily do it because it's constant q naught at all points. Q naught times the area is all I will get, right? So this can be easily the heat input, which is what I want. Minus q dot n, I can simply calculate by inspection, because that's the heat in. So I know that it is being heated. This would be q naught, which is the heat flux scalar, times will be the area. So the area here is the width times the length, which is z. That's the area to which it is transmitted. Plus I will get from the other side also the same. So there also heat is coming in, right? And it is being transmitted to the same area. So I can easily write this as simply 2 q naught times w times z. Only we have a factor 2 because both these sides heat is being provided, right? And they are the same. So what you can easily do is to show that this in terms of the dimension is variables, you get the following equation. Times theta d sigma. If I do this, then and substitute for theta here, I will get the constant C2 to be actually minus 39 by 2 dt. That I let you do it. If run out of time, so what I want to do is also urge you to do the second problem, which is a flow down the cylinder as well as flow through a slit, but instead of considering laminar flow, consider essentially turbulent flow or plug flow. So which means what he is saying is that dz is simply equated to v naught. That's in fact easier because you don't have the extra term 1 minus x by b or 1 minus r by rc. So for plug flow, the two problems are the analog of the cylinder and the slit problem, but considering a plug flow, which means a uniform velocity, right? So the procedure is the same, except that the dimension is, as he has pointed out, the Vz max will be replaced by V naught. You can easily verify that, right? And then the answers are given. You can easily verify. This is just a direct application of the procedures. Again, you have to have the asymptotic solution only, right? So all you have to find are the constants will be different, everything else is the same, right? The boundary conditions and so on. And this integral condition again will have a constant v. So this is actually a simpler case of the case that we have considered so far for laminar flow. Right? So I think you can easily do problem 2. Problem 3 we'll discuss briefly in the next class. That is the direct analog of the heating free convection problem that we encountered in the space between two balls, and this is now between two cylinders, right? So I haven't given the full answer, so if you go to virtual Lightfoot and look for the intermediate answer, but the problem is very much similar, but only now you are working in the cylindrical coordinates. So we will consider this and the fourth problem in the next class, and then move on to mass transfer. Are there any questions? You have to work this out. You know, this is a bit confusing. It's just the mechanics of working. You work one of these problems and work through the entire thing, starting from the, writing the equation first and then non-dimensionalizing it, working out the boundary conditions, right? And you should get to the correct answer.